Hello, guys. Welcome back. So, what we covered on Wednesday class was mainly the floating point in terms of storing, and we learned the basic system, which is just if I give you a symbol 1 byte, and then we learned how that 1 byte is going to be utilized to store a fraction number in binary, let's say 1.23. So we learn how to convert it. We learn what the system is. This is the sign, this is the exponent, and this is the fraction. So hardware-wise, this was our byte, the byte that we used. And we learn how to do that in a byte. But that is not realistic, right? This we just learn what is the biased exponent and how the bias exponent was obtained and everything. So if you have any doubt, please refer back to the video. You will see the details in there. So in this class, we're going to continue, and now we're going to move from the byte, which is a realistic system, to a realistic system. Okay, so if you want to store a floating point like this number right here in binary, there are multiple ways to do it. Okay, and since there are multiple ways, we need a standard. We need a way that all computers can understand. So we're going to focus on IEEE. All right, so if you look at the IEEE, this is what we call a single precision. So in the single precision right here, you have the same, what we learned, the same principles we learned in storing binary in a 1 byte. We're going to do the same when we want to store it in 32-bit. So you have a 32-bit, which is 4 bytes in here, okay? And here you're going to have your sign, you're going to have your exponent, 8 bits, and you're going to have your what? Your fraction. The only thing now you see different is what? Is you have 8 bits, right? So now you have 8 bits. Here you had 3 bits. Okay, in this part you only have 3 bits. And the exponents, the bias exponents happen to be 3. So we either add 3 when we store, or we subtract 3 when we retrieve. So here we have 8-bit. Remember when I said that this 3, it doesn't mean the number of bits, that it means the range. We have from -2 to 3. So the maximum number was 3. So we used it as the bias exponent. So you have -2, and you have -2, -1, and then you have 0, and then you have 1, and then you have 2, and then you have 3. Okay, so this is what we covered last time: negative, 0, and 1, 2, 3, 4, 5, 6. Okay, so but 2 to the power 3, because we have 3 bits, and here is going to be 8. So where are the other 2's? So that's what we talk about, the infinity, positive or negative, and not a number. Because with one parents, you can either say +0 or -0 with one parent. So the only 2 parents that are missing in order to add up to 2 to the power 3, we're going to get 8 parents. That's for the infinity, positive and negative, and for the not a number. Now you're giving me 8 bits, so that's 2 to the power 8. So I'm going to get 2, 5, 6. That's very interesting. Okay, so we will figure out what is the bias exponent right here. Okay, so here we know that the maximum, because we have a range, right? Positive range, and we have a negative range, right? So the positive range is going to go from 0 to 3. Negative range is going to go from -0 to -2. Okay, so it's going to go from -0 to -2. Okay, so keep that in mind. So we're going to have the same. We're going to divide this into 2 parts, positive range and negative range. But that's what you're going to get, right? So that's with 32-bit. All right, so if you want to look at the double precision, now you have 64 bits. Okay, so that's a lot. So this is the sign again, but now you have 2 to the power 11. That's a crazy number now. So your exponents can be, the precision can be better now. Okay, and then you have the fractions is 52-bit. Okay, and the same applies when you have double extended. Now, interesting, you have 2 to the power 16, which is going to be 32,000. So you have a very crazy number. Okay, so this is exactly what the common floating point representation using the IEEE. All right, so now let's look at the single precision. We're going to focus only on the single precision, but you should know also the double and the extended double. So this is nothing new. This is the sign. This is the bit. The only thing that we need to learn here, we want to know what is the bias exponent. Okay, what is the bias exponent here? Okay. For the 3 bits, we already figured it out. It was 3, but it doesn't mean the number of bits. Okay, and again, it means the maximum number. Okay, and then this is the significant. That is the fractions. You have 23 bits, and you have the exponent. So the bias exponent or the biased exponent is 127. Why? Because your range here is going to be 1, negative 126 to positive 127. If you count these together, you'll find them too. Let's say 126 with 127. So this is going to be what? 6 and 7. This is going to be 13, right? And this is going to be 5, right? And this is going to be what? This is going to be 2. Okay? But we know that if you give me an 8-bit, I have a range from 0 to 255, right, guys? So we have 2 patterns missing in here. Again, this is going to be positive or negative infinity, and then we're going to have not a number. So 2 patterns for not a number, okay? And 2 patterns here for positive and negative. So these are going to be reserved for those. So if your exponent is 127, that is the maximum positive, and that is the maximum of the lowest negative. Okay, so that's your range. So this is good to know right here, all right? So this is the single precision. This is our bias. It's important to know the 127. Let's look at this table right here. So if your exponent is 5, if you have like something 2 to the power 5, and you want to store this, okay, then you have to add the exponent to the bias, right? So the exponent right here is 5. You add it to the bias, which is 127. So we're going to get what in here? We're going to get 132. Convert this into a binary, and then you're going to find this number, right? So if you have 1, 2, 4, 8, 16, 32, 64, 128. Okay? So we know that's 128, and we know this is 32. This is going to be 32, right? So this is what the number is, if you can see it here. And this is the rest. Okay, so this is how what you should do. You need the bias. So the bias exponent, you need the bias with the exponent. You put them together, you get the bias exponent. Okay, so your bias exponent right here is 132. Okay, that's when you store it. You add 27. And remember, if you want to retrieve it, you just subtract what you added, which is 127. All right. So this is also something we already covered when we talked about the 1 byte. So that is normalization. If you forgot, just reminding you. So if you have this number, is this number normalized? No. So we're going to move this one, 1, 2, 3. So this is going to be 1 point, whatever the number you have in the fraction, 2 to the power 3, because we moved this point 3 places, right? This is here. We're going to move it to the right, right? So this is 1, 2, 3, 4, right? So it's going to be negative because we moved into this direction, negative. When we move the floating point to this direction, is going to be positive number. Okay, so that is the floating point. Okay, so just keep that in mind. So why we're doing this? Because we need a significant digit. Zeros are not significant digits. If you look at this number again, so this you have to keep moving it. 1, 2, 3, 4, 5, 6. So now you have only one single digit. Significant digit. Just look at the formula we covered in the last video. Okay. So this is exactly what you're going to have. So now we have this normalized number. Can we store this number? Of course. The basic idea is just we don't need to store 1, if you remember, because we know 1 is going to be always there. So if we look at the let me see if I can do it better. If you have like the single precision, when you have 1 for the single precision, and you have 8 for the for the exponent, and you have 23 for the fractions. You need to remember this very well, and you need to have it with you. Okay, so we know this number is positive, so we're going to have 0. We don't know what the exponent is, but we know the bias how to compute the bias exponent. So we're just going to say, what is it right here? It's going to say 6 plus 127. So this is going to be what? This is going to be 133, right? So this is what you need to convert into a binary, and you need to store right here. So this is 128, right? And this is going to be 0, 0, 0. right, guys? And then 0, we're going to have a 4, that's 32, 0, 1, right? I'm sorry. So this is 128 with 4, 132 with 1, 133. So this is the number that we need to store in here. So we're going to have 1, 0, 1, 0, and then 0, 0, 0, 1. That's my exponents. And the rest is going to be the fraction. So it's going to be 0, 1, 0, 0, 0, 1. And we have to continue until the bit 23. You have to do that. So in this case, if you want to go with zeros, just keep adding zeros in here. So you have to show me that you know you need to add it 23 bits. Okay? You can play with this with the other examples right here. So this is a negative number. I'm gonna show you cases in there, but you're gonna do this again. You're gonna say -4 plus 127. So this is here when you're gonna get a positive number, but less positive number, right? So this is gonna be 123. Okay? And then you're going to convert this and you store it. And since this is a positive number, you're going to have 0. You store this exponent, and then you have the fraction. You got the idea, right? Okay, so if you have this number and you need to store the floating point binary value, so this is the way it's expressed, right? So now let me see. So this is something that they already taught you in the school. I mean, when you start learning computing, introduction to computing, they taught you how to convert fraction numbers into binary, okay? So, or from fraction binaries into decimal. If you forgot or you feel like, no, I didn't, so just go back and look at your introduction. It must be there, introduction to computing or introduction to computer science, okay? These are very basics. A lot of YouTube videos in there, and if you have any issue, come to my office hours, I can explain. But this is like the fundamental way. I'm not gonna follow this because I know you know it, or I assume you know it, but it's straightforward. First, we're gonna look at the whole number. So this is 1, 2. 1 plus 2 is gonna be 3, 1, 2, 4, 8, right? So this is gonna be 3. So we figured this one out, that's easy. But we wanna figure this number out. So all you need to do, since you're gonna start from here, right? So you're just gonna say 1 multiplied by 2 to the -1, right? You with me? So here it's gonna be 1, and that is the number, 1, 1, that's the whole number, and then you have 1, 0, 1, 1, right? So right here, you're just gonna start with 1 to the point, you multiply 1 by 2 to the power -1 plus 0, okay, to the point -2 plus 1 to the -3, and so on and so forth. So you're gonna go with negatives. Why are you gonna go with negatives? Because you have 2 digits in here. This is gonna be 2, right? Sorry, this is gonna be 1, and this is gonna be 0. And after here is gonna be -1, -2, and so on and so forth. Okay? So if you look at this, this is gonna be nothing but 1 multiplied by half, right? That's what 2 to the power -1. Okay, plus then that is gonna be a 1, or sorry, 0 multiplied by quarter, right? And so on and so forth, okay? And if you add the fractions up, this is what you're gonna get, the number. All right, so this is exactly what the number is. If you multiply all of them together, this is what you're gonna get. All right, but I will show you a very simple way to do this. Okay, so if you give us this number right here, we can figure out a way. So we know 1 here is gonna be 3, no brainer. 1, 2, and there's gonna be 3. So now we need to figure out the fraction. So how many digits we have in here? 1, 2, 3, 4. So 2 to the power 4 is what? 16. So that's the denominator. Okay, what is this number? 1, 2, 4, 8. So that seems to be what? 11, right? Am I right? This is 8 plus 2 plus 1. That's it. I don't need to do all of this. I will show you more examples later. But if you give me this number, I'm just going to get the whole and then the fraction 2 to the power, whatever the number of digits we have in here, 4, then 2 to the 4. That's the denominator. And then you just look at the fraction and convert that into the decimal number. So this is what you're going to get. This is good enough in the quiz or in the exam, okay? But I'm not, since I'm not using calculators, so I'm not going to ask you to provide me the value. I'm just asking you to provide the fraction, all right? But this is exactly what it is. So this is what I was talking about right now. These are multiple examples. So if I look at this number, I know this is 3, no brainer, right away. But I have 2 digits in here, right? So I'll say 2, just let me go here, 2, and I have 2 digits, 2 to the power 2, this is going to be 4. So the denominator is going to be 4. And what is this number? 1, 2. So this is 1, 2, 4, 8, if you remember. So this is 3. So this is going to be my number right here is going to be 3. And if you want to put that, that's fine. Okay. If you look at this number right here, this is very interesting. This is a larger number, right? So this is going to be what? 1, 2, 4, 8. So this is 12 and 1 is going to be 13, correct? So this is going to be 13. And what is the fraction? 1, 2, 3, 4, 5, 6. So it's going to be 2 to the power 6. What is 2 to the power 6? It's going to be what? 64. Okay? And then what this number is. So this is 1, 2, 4, 8, right? 16 and 32. So I have 32, right? Plus 4, correct? 36. Am I right? Plus 1, 37. So that's what you have right here. And the same applies. For this one, it's going to be always 1. Since this is 0, we're just going to say assume it's 1. Okay? So if it's the denominator right here, so here it's no-brainer, right? We're just going to have 1 and denominator, and then the denominator just count these 1, 2, 3. So 2 to the power 23. So it's going to be a crazy number. Okay, guys? Okay, if you feel comfortable with the method that you learned in Introduction to Computing, please go with that. But this is something I feel fast and handy for me, but I don't know about you, okay? So this is another example right here. If I give you a half in here, I say this is a binary converted into a decimal. Again, 2 to the power 1 is going to be what? It's going to be 2, right? So that's going to be my denominator. Okay? And then what is it that I have, right? So it's going to be always 1 since we don't have a value right here, right? So this is going to be a half. So this is what we call decimal fraction. If I ask you for the decimal value, that's a different story. But now I'm asking you for a decimal fraction. This is good enough. You don't need a calculator, so you should do it. Decimal value, if something simple, I will ask you for it. But if it needs more than the basics, then I'm not going to ask you for that, okay? So we're going to focus on the decimal fraction. If you give me this number again, so this is 2 to the power 2, right? So for this example here, this was for this example. Okay, so 2 to the power 2 is going to be what? 4. So now I'm going to have what? And this number is what? 1. So this is going to 1/4. This number 2 to the power 1, it's 2. And we know this is the only one we have right here. So that's a 1. You get the point, guys? How about this number here? So we know that the numerator is going to be 1, but how about the denominator? So 1, 2, 3, 4, 5, 2 to the power 5 is going to be what? 32. So this is going to be the decimal fraction. These are very important cases. Okay. So here is the other way around. We are not giving you binary now. We are giving you decimals, right? We said, okay, this is the decimal. How are you going to get it back? Okay, so this is the quarter. How are you going to get it back into a binary real, right? So this is reverse engineered, right? So if we see this right here, we're going to say 2 to the power 2 is going to be 4, and this is 1/4, right? That's what we did it in the beginning. Now we want to reverse it. If I give you this number now, and I say, what is the binary? So you're going to say, what is it that if I have it as a power of 2 is going to give me 4? It's 2, right? So I need 2 digits. I don't know the value. And then here it's a 1, so it's going to be 1, 0. So that's how you're going to get it. Okay, so this is 0.01. How about this number right here? Okay, so what is it that if I have as a power for 2 is going to give me 8? So I need 3, right? So I have 3 zeros now. I know I have 3 digits. How to represent this 3? We know this is going to be 1, 1, 0. So this is going to be the representation of this decimal fraction in terms of binary, right? So this is what we have in here. So you should be able to do that, okay? All right, guys, is that clear? You can follow the book. This is what the book is using here, but I'm just showing you a simple way to do it. So this is 7 again. What is it that you have a power that's going to give you 8? So you're going to say, I have 3 digits right here, okay, for this part. Going to have 3 digits. So, but what to fill or how to fill those digits? What's the denominator? It is the denominator right here is 3. So again, we're going to have 1, 1, and this is 0.0. So this is what the value is. Okay, you can do it for the 16. How many bits that if I have, I mean, what is it that I have as a power of 2 to get 16? It's 4. So I'm going to have 4 digits here. Okay, for this example right here. And I have a 5 in here. So this is going to be 1010.0. So this is my 5 here. Okay, guys, this all works good if the denominator is a multiple of 2. But if it is not a multiple of 2, then how are we going to do it? Okay, but if this is not a multiple of 2, then how are we going to know the fraction? I will show you that in a minute, okay? Cover that in a whole slide. Okay, so this is bottom line. This is what it is. It gave you this number. It's normalized. Exponent is 0. So the number is positive, so we're going to have the most significant bit as a 0. The exponent is 0, so 0 plus 127. So that is my exponent, and that is my bias. Okay, and both, they're going to be what? The biased exponent, right? So we add this to this, that is the result. So the result is going to be 127, and this is in binary, right? And then this is the fraction I'm given right here. So this is how you're going to store it. Okay, and remember to have this 23 bits. Okay, so this is exactly what you see right here. All right, so that is hopefully clear in your mind now. And these are multiple examples right here. So if you're given this binary number right here, and you know it's a positive number, so the sign, it is going to be what? 0. Okay, but is this number normalized? No. Then we're going to do what? We're going to move this 1, 2, 3 right here. Okay, so it's going to be this number 1.101101 multiplied by 2 to the power what? 3. Okay, so this is my exponent, and the number is now what? Normalized. So we have to normalize it first. Okay, so we have to normalize the number here first. Once we normalize it, then we get what? We get the exponent, and then we add the exponent to what? To the bias. Okay, and then we're gonna get the biased exponent. So this is 130. So I'm gonna go here and store it. How to do 130? Remember, just say 1, 2, 4, 8, 16, 32, 64, and 128, okay? So this is 128, this is 2, this is 0, 0, 0, 0, 0, 0. So this is gonna be the number, right? So you're gonna go and store it here, 1, 0, 0, 0, 0, 1, 0. 128 and 2, 130. And how about the fraction? We're just gonna take this number, 101, 101, right? So this is what you see, 101, 101, and then the rest are gonna be zeros. They're gonna be 23 bits. Keep that in mind, okay? These are 8 bits, and this is just 1 bit. Okay, guys, so play with this number again. So why this is 120? Because you have to normalize this, right? So this is 1, 2, 3, 4, 5, 6, 7. Okay, so you move to the right, so that is a negative, right? So it's going to be -7 plus 127. So that's going to give you what? 120. And that's what you have in here. Okay, so if that is the case now, then you have, you know, the number is positive. You know this 120, you convert this into a binary and you store it here. Convert the 120 into a binary like the way we did in here. And then you're going to have just the fractions along with the zeros. If you count these, you're going to find them 123 bits. Okay, so the exponents is known after the normalization. This is a fact, so you have to understand that, right? We don't know the exponent here. Here the exponent is clear because the number is normalized. So the bias exponent was 127. The bias exponent here is not going to be known until we normalize. So that way we're going to get the exponent. And then we add the bias, which is 127. And then we're going to get the bias exponent. Okay, guys? So this is what I was talking about in the beginning. So this is 0, this is infinity, and this is not a number, okay? So every one of them has a one pattern, if you notice. So this pattern and this pattern is identicals, right? The only thing is the bit sign right here. Everything else is the same. You're just gonna change that bit from 0 to 1. So you need one patterns, but changing that bit. So this is when we did the 250, we did the 253, and we know that we are missing 2 digits to make it 255, right? Because that is the range if you give me an 8 bits, right? You with me, guys? Because that's the exponents for the single precision. So the single precision have 8 bits in here. So 2 to the power 8 is going to give us 255, but the numbers we saw is 253 because the 2 were already given to what? To the infinity and not a number, because 0 has been taken care of already. Okay, so the same here is going to apply for what? If your exponent is all 1, you might see this in your test. That shows you that this is in the sign bit. Okay, so that's your sign bit. That is your exponent. That is the fraction. So if you see the fractions are all zeros and the sign bit is 0, but the exponent is all 1, you know this is a positive infinity. This is something beyond what the fraction can do. If it's a negative, the same thing, but this is going to be the sign. Okay? The same for not a number. So we have 2 types of not a number. It's quite not a number, and we have is not a number. Okay? So if you do Java programming, you maybe have seen this when you play with the fractions. So this is the error message, especially if you do debugging, that's what you're gonna see, okay? So both of them here, we don't care. X means don't care. If it's 0 or 1, we don't care. All we care about that the exponent is all 1s, and the first bit, we don't care about these. They could be any number. But the first bit in the fraction is 1, then we know this is quite not a number, okay? Is not a number. This is the signifying significant field begins with a 0, right? So that is when you see it here. This is begin with a 0. If it begins with a 0, then we know this is the significant not a number, not a quite not a number. Quite not a number. They have 2 different ways to debug them and to correct them. It depends on the operation you are doing. So this is very important. If you do real number manipulation or computations and you get an error, so this is going to tell you something very important about the microprocessor you use. Quite not a number. Just try to look at some examples when you get to the point when you deal with the real numbers in Java, and you will see like a very simple way to play with it. But right now, I just want you to know this is the way we represent them. Okay. So if we want to convert a binary number now into a decimal, this is going to be your algorithm. Just follow those steps, okay? So you have the most significant bit is the negative or positive. You know the 8 bits. This is for the single procession. Please remember this word, not double, single procession. That means you have 32 bit, okay? 32 bits. All right, so we know this algorithm. We know how to convert. We played with this a long, for a long time, right? So we know this is the sign, this is the exponent, and this is the fraction. If I give you this number right now and I say, what is it in decimal? How are you gonna convert this into a decimal number? So if you wanna do this, the first thing we have to look at the sign. Is this positive or negative? In the test, you are not gonna see them in colors, so you need to figure them out. When I give you a binary number, count the first 0, draw a line, then count 8 bits, draw a line, and then 23 bits, and then draw a line. So that way you will know it. Please do this in the test, okay? You're not going to expect me to provide you with the colors, okay? Because I assume that single procession, and you know this format, IEEE format, okay? If that is the case, then now we know that this is the bias exponent, so we want to reverse it back. We know that the bias is 127. Okay, we know that, right? So we're just going to look at this number. So this is 128 plus 2, that's going to be 130. And we know that is going to be my what? My bias exponent, not biased. It's the bias exponent. So since I add to store, I subtract to retrieve. So I'm just going to subtract 127. Then I'm going to get the 3. So that's going to be my what? That is my binary 3 here. So this is going to be my exponent. So I know the exponent stored right here is 3. It's not 130 because 3 added to 127. We get it 130. So we want to get it back. We just subtract 127. We're going to get the 3. That's the system. Okay? So now we need to combine the sign, the exponent, and the significant, right? So we know we don't have a 1 right here, right? Because we know 1 is always going to be there. Remember, we are not storing 1. We assume it's there because significant bit and it's binary. We only have 0 and 1. 0 is not allowed to use. It's always 1. Why do I need to store it? Use that bit for the sign, so you're going to have more bits for the exponents. Okay? So this is exactly, we're going to come up from outside 1, and this is my fraction. Significant fraction here, guys. What's the significant fraction means? Just the numbers that they have 1. So 0, 1, 0, 1, 1, 1. And these are all zeros. They are insignificant. Take them off. So it's going to be 1 point, this number, 0, 1, 0, 1, 1. Multiply by 2 to the power 3. You see what I'm talking about, guys? Okay, so we got the 3 from the exponents, we got the fraction from the significant, we got the sign from the first bit, and the 1 we added because we know it's going to be there all the time, since it's a binary conversion, right? So the next step right now, I want to convert this into what? I want to get this number into its decimal format. So I have to do what in here? I normalize the number. So I'm going to do what in here? And normalize the number. So how are we going to do the unnormalization? So I know that this is the number right here. So I need to move this. So I'm going to see 1, 2, 3, because the exponent is 3. If I do it, it's going to be what? 1, 0, right? 1, 0. And then we're going to have what? 1, 0, 1, 0. And then the dot is going to go there. That's when you have it right here. And then we're going to have what? 1, 1. So we normalize the number. We get it back to its form. So, and this is a positive number. Now we're going to go back to our own rule that we just learned right now. So this is the whole number, right? So what is this? 1, 2, 4, 8. So this is 10, right, guys? And what is this? So what is it that if I have 2 to the power 2 is going to be what? 2 to the power 2 is going to be what? It's going to be 4. And what is this number? 1 plus 2 is going to be what? 3. So this is could be 10th. And we have the third quarter right there, right? So this is what the fraction value is. And this is what the decimal value is, okay? So this is in fractions. So that is it. That's exactly what it is. So get this one as a whole number, converted into a decimal, and it happens to be a 10. Just use the rule 1, 2, 4, 8. And for this number, 2, you have it. You have 2 digits. 2 to the power 2 is going to be what? 4. So I know that is going to be, the denominator is going to be 4. And then the number right here itself is 3. So I know it is 3 by 4. Okay? So this is how you convert from a binary into a decimal. Okay? So now converting a decimal into a binary, right? So this is going to be a little bit different, okay? So let me show you the example right here. So I'm giving you a decimal right here, okay? And then I want you to convert this into a binary. That is no brainer. That's easy, right? So the first thing that I can do, I can play with 19, and then I can say 1, 2, 4, 8, 16. So this 16, 18, and 1, 19. So I have 19, but I have 3 in here. Okay, so 3 is not multiple of 2. Okay, so I cannot easily convert it if it's not a multiple of 2. Okay, and hence we can use what? Converting the fraction to a binary reals. Like, but what to do then? Well, you have 2 ways. You either use the long division. This is the method the book uses. Or you use the multiple of 2. This is the method I like. So I'm going to cover this part. Okay, if you like the long division, please refer to the book. Okay, so this is exactly what we're going to do in here. We know that the number is negative, so we have the negative sign in here. We know how to convert 19, so that's my 19, but I have no idea how to do what? How to do the 3. Okay, so let's first figure out, because since 19 is easy, let's figure out how to convert not a multiple of 2 number into a binary fraction. So the multiple of 2, you're just going to say 1, 0.3, and you multiply it by 2. So you're going to say what? 0.6. So the value you got out of here is going to be 0. Okay, and then you're going to go to the second. So it's going to be 0.6 now, multiplied by 2. This is going to be what? 1.2. That's 12, right? So we're going to have a 1 in here. We take this one in here. We take this one, then now we have 0.2. We multiply it by 2. So we're going to have what? 0.4. So this is, again, we're going to get a 0. Okay? And then again, I'm going to get 0.4. I'm sorry, 0.4. We multiply it by 2 is going to give me 0.8, right? So I'm going to get a 0 right here. So then I'm going to get 0.8 multiplied by 2. Then I'm going to get what? I'm going to get 16, 1.6, right? So I'm going to get a 1 in here. Okay, so now I'm going to get 0.6 multiplied by 2. So this is going to give me what? 1.2, and this is going to be a 1. But bingo, I already have seen this before. That's the pattern. So I'm going to repeat myself. That's the idea of rounding, if you remember, in real numbers. That's why they round, because pattern is going to repeat again and again and again. So if you look at this number now, you're going to have 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 1, 1. Do you see what I'm talking about? So this is going to repeat forever. So this is the number that's going to repeat, 1, 0, 0, 1. So every time you have 0, it's going to be like here, 0, this 0. Let me see it right here. And then we're going to have 1, 0, 0, 1. And then 1, 0, 0, 1, 1, 0, 0, 1. So this is the repeated pattern. So you need to keep a star in here because you will need it later. But do you see the idea right here? Okay. So if that is the case, then we're going to go back right here. We're going to look at the number right now. So I know this is 19, right? This is how we converted 19. So here we're going to have 1, 0, 0, 1, 1, point, right? 0, 1, 0, 0, 1. I know this, and I can repeat it as much as I want, but for now it's good enough. Okay, so this is my pattern, 0, 1, 0, 0, 1. Okay, and then 1, 0, 0, 1. So it's going to repeat again. 1, 0, 0, 1. It's going to go forever. 1, 0, 0, 1, 1, 0, 0, 1, and so on and so forth. I don't want to do it. I just want to keep it this way. So we need to normalize it. So this way we're going to say 1, 2, 3, 4. Right? So it's going to be 1.001101 multiplied by 2 to the power 4. So we normalize the number. Okay, once we normalize the number, then now we need to find the exponents, right? So we know it's 4. We figured out the exponent already. So we know we have the exponent plus, we know it's a single precision, right, guys? If it's a single precision, we know the bias is 127. And we are looking for the biased. Okay, so if we add this, we're going to get 131. Okay, so now I get my exponent. Okay, and I know my fraction. This is going to be my fraction. Keep that in mind, please. Okay, so it's going to be 0, 1, 1, 1, 0, 1, 1, 1, 0, 1. Okay, so this is my fraction now. Okay, so if I do this part right now, if I can do this part right now, then now I have everything I need, right? So I know the number is negative, right? So let me show you that. So I know the number is negative. So here is going to be what? It's going to be 1. Okay, this is the way I write 1. Okay, so this is going to be 1. What is the exponent? Is 131, right? So it's 131. Let's just figure out how to convert this into a binary. So I know this is 128, right? This is 0, 0, 0. This is 64, 32, and 16. And I know that this is 8. This is 4. I need 2, right? So 2 here is going to be a 1 because 128 here and a 2, that's 30. And we need the 1 here, right? So this is 131. So it's going to be 1, 1, 0, 0, 0, 0, 0, what? 1. So this is the exponent. So here I'm going to have 1, right? You with me, guys? 1, 0, 0, and then I have what? 0, 0, 0, 1. So that's my exponent. What is my fraction? So I know this is my fraction. So I would say 0, 0, 1, 1, 0, 1, 0, 0, 1. And these are not 23. I have to have 23. 1, 2. Let me divide them in this way. So this is not a 1, okay? This is just the line, okay? Okay, so if that is the line that I have right there, then now I need the fraction, right? So for the fraction right here, I'm going to have what? I'm sorry, I'm going to have this 1, 0, 0, 1, 1, 0, 1, 0, 0, right? Take this one off, I'm sorry. Okay, let me erase this. Do I have the eraser here? Okay. So let me get rid of this. Okay. And okay, this is getting a little bit. Okay. All right, so then these are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but I know I need 23. So I will repeat this pattern. So I'm going to say 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. So this is going to repeat until I get to the bit number 23, okay? So you need to show me that, please, when you do your solution. Do not just say, write the number 5 bits and you're done. No, the fraction here says 23 bits. Just look at it. Okay, so you have to fit it with 23 bits, okay? Is that kind of clear, guys? Okay. So this is basically what the floating point numbers, and this is the way we store the floating point numbers. Okay. Hopefully now you have an idea of how x86 does it, especially for a single precision for a 32-bit. Okay. Just remember that the 8-bit that I use, this is an image, this is an imaginary computer, is not a real computer. But that's hopefully helped you to understand the idea of what is a sign, what's an exponent, what's a fraction. And then I hope now you understand what's an exponent. And when you add an exponent to a bias, what's a bias, how to get to the bias, and how do they derive the bias. And when you add them together, you get a bias exponent and how you store it. And then you know the fraction. Now you also know if I give you a binary number stored in a single precision, you should convert it into a decimal. Or if I give you a decimal number and I say it's stored in a single precision, you should be able to do that easily. Okay, let me just introduce you to the floating point unit, and I'm going to stop a little bit, and then we're going to continue the other part of the floating point. So now we know how to store a number and everything. We just want to look at the FPU, the floating point unit. Okay, so we're just going to look at it. What is the concept in there? So what we have covered so far is the general purpose registers, okay, like EAX, EBX, and ECX, and so on. This is the instruction pointer. This is the E flag register, right? And these are the multimedia. We did not cover those registers. They are for the multimedia, so we did not cover them. And now we're going to cover the floating point. So next to those registers, this is your CPU, okay? The whole box right here is the CPU. All right, and then now we're going to focus on x86. So if you notice in here, it has a different registers. And if you notice in here, it has its own E flag register and everything. So it's a completely, it has the status and everything, okay? So this is a completely different unit, and it has its own instructional instruction. It has its own instruction, it has its own arithmetic, it has its own registers. It's a completely different unit. So we are moving out of this part. Okay, we are focusing here. Hopefully, if you do embedded system in the future, you're going to learn more about these, okay? But you're not going to cover them now. So the whole idea now, the FPU does not use general purpose register. It has its own registers, okay? And instead, it has like those registers, R0 to R7. Okay, so register 0, register 1, 2 to 7. So it's very close to the ARM, but it's very unique. You're not going to access registers using this R0 name. You're going to use the ST. Okay, that is the stack. We will see what is the stack. Okay, but one fact that you need to understand, if you look at this part right here, it is an 80-bit register, right? So it's an 80-bit register. It has a big size in there, okay, big storage. All right, so we have 8 of them. All right, and we always have this like system, which is the software kind of, okay, it's not a real hardware, and the ST0 always point at the top of the stack. So those registers are designed in a stack way. So this is the top of the stack. We don't care. The top right now is R3. If we push another value, maybe the top is going to be another thing, okay? But ST0 is always going to say, hey, this is the top, okay? So this is the 3 that you see, the number right here. That's going to tell you the top of the registers. Okay? So if we want to load data, or we want to store data into those registers, we're going to load the value from the memory. So if you move things from memory to registers, that's loading. It's very important. Okay? And we can also perform some calculation, and we can store stack values into the memory. So here we're going to get it from the registers to the memory, and we're going to see different instructions. So we have store instructions, and we're going to have load instructions. When you say load, the load doesn't know how to move from register to memory, just from memory to register. Okay, so this is something that we're going to look at. The other thing that you need to understand that the floating point unit, you will see that in the lab, it works using a different system, right? So this is what you call the infix, I'm sorry, and the postfix system. Okay, in the infix system, this is what we usually do. We get 5, and then we say multiply, and then we say 6, and then we subtract and from 4, and then we get the result. When you use the postfix system, which is many calculators use this system, first we have to push the data and then call the operation. So it's data and then operation, data and then operation. Okay, so you first push the data 5 and 6, and you're going to say, okay, I have them already. What do you want to do? Please multiply them. So you give me the operation. Okay, so you have data, data, and then operation. Now you have one. The result of this now is a data. Okay, and then now you have another data right here, and you have an operation in between, right? So just this data is already there because already on the stack. What I mean by the stack is those registers. Do not go to the stack that we just covered in chapter 5 and 8. So what we're going to do right here, we're just going to say, okay, we have this data there, and we have this operation, we have another data. So we need to push this data. So we have to push this data, and we call what? We call this operation. So subtraction, what from what? This data that we already stored from the data that we push right now, we're going to subtract them, and then we're going to get another data. So now we're going to get the final result, which is the data, the final data of the operation. Do you see it? I think you are aware of this. It's covered in many classes, programming classes, but this is something we're going to use in this class as well. I believe it's in Java 1 or Java 2. They also teach this, or maybe in data structure. I'm not very much sure. But this is what we're going to do. It's A plus B, and then we do what? Operation. We are not going to, we say push A, push B, okay, and then call the operation. So it is something that we already covered, if you remember, in chapter 1 and the chapter 0, the big picture, beginning of the semester. We have one of the architecture, which is the stack and the accumulator, if you remember. And then we have the register, and then we have the memory register, remember? So that's how the stack works. This is the register. This is how the FPU works. It works using a stack register, okay? If you look at this operation, push A, push B, subtract, push D, and then divide. This here, this is like push A, push B, and then what? Add. So now you have a result right here, okay? Then push C, push D, and then add. So you have a result right there in the top of the stack. So the stack, if it's like this, this is A minus B, and this is C minus D. I'm talking about the result. And then now you're saying what? Multiply. So this is what you see. AB, you're going to get the result after you add it. You have it here in the stack. And then CD, and you call this, and then you have the result. Now you're going to say what? Call multiplication. So multiplication knows where it goes. Okay, it knows exactly where it goes, where it should go, and then it's going to find the value in here, just going to say pop, and then do the operation. So the ALU assumes that the values are already being entered into the top of the stack. So this is very important, and if I give you this example right here, I will explain it right now. So this is when you say 5 by 6 minus 4, we know push, multiply, push, and then subtract. So this is exactly what happened. So this is the system. Just focus on those 3 things right here. So this is what we have. The left, right here, we need to push it. So if you push it, that's the top of the stack, always pointed at by ST0. Okay, so we pushed what? We pushed 5. Now we need to push what? We push 6. So now we're going to push 6. If we push 6, what is the top of the stack now? It's 6. Because 5 now is no longer the top of the stack. It's going to be ST1. Is this R0, R2, R3? That's the beauty of Intel FPU. We don't care. We just know it's in a register. Okay? So now we push this and this. Then what's next? That's the action. Push and push. Now what we're going to do? Now what we're going to do, we have to call what? We have to call the multiply, right? So now we're going to say multiply ST1 by ST0. So we multiply ST1 by ST0, right? And pop ST0 of the stack. So once we do this, when we multiply this, we're going to get the result into the top of the stack. Keep that in mind. Mul instruction is going to do this, but we will see type of mults like the ones that you're going to see in the lab. They're going to work a little bit differently. Okay, sometimes they don't pop, so we have to force them to pop. Okay, so if we do this, we're just going to say load maybe 5, and then we're going to say load 6, and then we're going to say fmul. I will show you that. So the ALU now, it doesn't care about loading, so we have to do it as a programmer. And then now we are calling the ALU. So ALU assumes the stack has 5 and 6. Just gonna do the multiplication and pop, because this is how it works when it sees no argument in here. Because you might ask, oh, where are the operands? This instruction doesn't have operands. It assumes the operands already on the register, on the stack, I'm sorry. Okay, so now we have the top of the stack as 30. What we're gonna do next, we're gonna push 4. So we push 4. What is the top of the stack? No longer 30, it's what? 4. And then we're gonna call what? Subtract, right? So we're gonna say subtract. So we're gonna subtract ST0 from ST1. So we subtract this from this, right? And we're gonna pop. So when we subtract this, we're gonna get 26, and that's gonna be the top of the stack. So you'll find the result in the top of the stack. Okay? So this is how the x86 floating point unit works, guys. Okay, so I'll stop right here, and I'll continue later in covering how push and pop works, and then we're gonna finish up this this chapter. All right. So I'll let you go for now, and hopefully you guys have a good experience with quiz 6. I know the some of you maybe have some issues with the stack, but believe me, it's always a challenging question for like the past many years I've been teaching this class. But the bottom line of that quiz is just to show you that there is always another level that you need to push yourself to, okay? So if you haven't got the point out of it, I will try after we graded the quiz 6. In the final review, I will go over that question in case if you still have some issues with the stack, all right? So for now, I will just see you in the next time. All right. Thank you, guys. Bye.